Good morning, all of you. Any questions from whatever has been covered so far? Please note that we covered all that is required, all the background that is required to solve two-dimensional boundary value problems. So in today's class, we are going to look at application of whatever we learned to related to structural mechanics problems. And please note that in reality, all the problems are going to be three-dimensional problems, but under special conditions, when the applied loading as well as geometry of the particular structural component that we are actually trying to analyze, it satisfies certain conditions, we can reduce the dimension of the problem. In the sense, three-dimensional problem can be approximated as a two-dimensional problem, making certain assumptions that strain, out of plane strain is zero, or out of plane stress is zero, such kind of things, or the stress is symmetric about the axis, or if any of these conditions are not applicable, then we need to solve full three-dimensional problem. So in today's class, we are going to look at one such kind of simplification, and you must have studied as a part of your advanced structural mechanics, okay, or advanced mechanics of materials or mechanics of materials. You must have heard about this plane stress and plane strain. And really, there is nothing like two-dimensional elasticity problem. In the sense, it's an assumption that stress is the stress components are in-plane stress components are dominant than out-of-plane stress components. Then it's called plane stress, and in-plane strain components are dominant over out-of-plane strain components. Then it is plane strain. Okay. So in today's class, we are going to look at plane stress, plane strain cases. Why we are looking at plane stress, plane strain? Because we can simplify the three-dimensional problem as two-dimensional problem. So whatever we learned, we can easily apply, because we just now we noted how to solve a two-dimensional boundary value problem. So we can easily solve this. So as I mentioned in the last class, by the end of this week, we are going to complete this course, at least teaching, and exam is going to be on 15th, May 15th, Saturday. So in today's class, I'm going to quickly go through this plane stress, plane strain problems. And for that, you require all the background for solving two-dimensional boundary value problem that we covered in the last classes. So now let's go through this two and three dimensional elasticity problems are governed by system of coupled second-order differential equations. So far, whatever we have looked at, two-dimensional boundary value, general two-dimensional boundary value problem, we looked at how to solve a second-order differential equation. So we can directly apply those concepts here. So that's what is mentioned. Two and three-dimensional elasticity problems are governed by a system of coupled second-order differential equations. Okay, the main problem variables are the displacements along the coordinate directions. So the displacements in two-dimensional problems, you are going to have two coordinates. So you are going to have two components of displacements along each of the coordinate direction. So the main variable that needs to be determined is displacement along the coordinate directions. Once the displacements are known, stresses and strains can easily be calculated. And this whatever lecture is going to present finite element formulation for two-dimensional elasticity problems. Okay. So that is the title here, two-dimensional elasticity. So now we know if a second order differential equation is given for the two-dimensional case, we know how to proceed using variational method or Rayleigh-Ridge method or Galerkin method. So now for elasticity problems, under the assumption of this plane stress or plane strain, three-dimensional elasticity problem can be simplified as two-dimensional problem. And then what are the various differential equations that we are going to get? We need to make a note of it so that whatever concepts we learn, we can easily apply that and get the element equations. Okay. So the governing differential equations, a general three-dimensional elasticity problem involves three-dimensional stress state. So a general three-dimensional elasticity problem involves three-dimensional stress state with components identified as sigma normal stress components and shear stress components. Sigma x, sigma y, sigma z are the normal stress components, and tau is usually used to denote shear stress. So tau xz, tau zy or yz, tau xy are the shear components, where first three are the normal stresses and the last three are the shear stresses. Corresponding to these stress components, there are 6 strain components. Two special cases of significant practical importance are what are called plane stress and plane strain cases. So for a three-dimensional elasticity problem, you are going to have 6 independent stress components, out of which 3 are normal stress components, 3 are shear stress components. Corresponding to these stresses, you are going to have strains. So 3 normal strains and 3 shear strains. Okay. Usually strain is denoted with epsilon. Okay. So wherever sigma is there here, you replace with epsilon, you are going to get 6 strain components. And so here this two-dimensional elasticity problem can be simplified into two-dimensional case and 2 special cases of significant practical importance are what are called plane stress and plane strain. So what is plane stress? When analyzing thin plates subjected to in-plane forces. So here you can see here there is a plate shown, and please note that when I say plate, don't think we are going to discuss about plates and shells. That plate is different. Okay. Here imagine there is a, you can see here it's looking something like a projection, a cantilever beam. Okay. It's not really cantilever beam, and it is fixed here. The structural member is fixed here, and the structural member has the dimensions. You can see the dimensions. If the length of the member is taken as this direction, length and width of the member and thickness. So all three dimensions are there. Even though thickness is small compared to other dimensions, and one end of this member is fixed here, one end of this member is fixed here, and you can see how the loads are applied. Loads are applied in this plane, in the plane consisting of these 2 major dimensions, length and width. The loads are applied on a plane which is parallel to the plane consisting of these 2 two major dimensions, length and width. Okay, so load is applied in this plane, in the plane which is coming out of that particular where it is fixed. It is applied in this plane. Load is significant, or load is applied in this plane, and thickness is small compared to the other dimensions. Okay, so please make a note of this one. And you can see here how the load is applied. Load is applied on a particular plane. Okay, so now let's once you have noted this, let's see the description of this, how it is given here. When analyzing thin plates subjected to in plane applied forces, so the forces that are applied are in plane, in the plane of the plate or in the plane of the structural member, and it is reasonable to assume sigma z and shear components having this z axis. So tau zx, tau zy. These are 0. So thing is, z-axis is going out of the plane of this member in this direction, and x-axis you can assume it to be along the length of the member, and y-axis you can assume it to be along width of the member, and z-axis along thickness of the member. So significantly, the load is applied in the plane of x and y axis. There is no load applied along z-axis. Load is applied along an axis or the plane which consists of this length and width. Along thickness direction, load is not, or a plane which is consisting of thickness direction. Along this direction, load is not applied. So load is in plane, in the plane of x and y. So what I'm saying is, you take this, the axis which is along the length of the member as x-axis, take the axis which is along the width of the member as y-axis, and take the axis which is along thickness direction as z-axis. So load is applied along xy axis, that is in plane. That is what is in plane. When analyzing thin plate subjected to in plane applied forces, what is the plane along which these forces are applied? X and y plane. And what are the stress components which consist of the other direction? One normal component sigma z, and two shear components zx, tau zx and tau zy. These are going to be almost negligible, or these components we can ignore them, neglect them. So it is reasonable to assume these out of plane stress components are 0. The non-zero stress components are sigma x, sigma y, and shear tau xy or tau yx. Tau xy is going to be same as tau yx. Otherwise, your equilibrium condition is not going to be satisfied. Why tau xy is equal to tau, or tau xy is equal to tau yx? Why it is so? You need to go back to your mechanics of materials. If you are not clear on that, that is what is called complementary property of shear. Okay, so plane stress, these are the stress components which are 0, and non-zero stress components are sigma x, sigma y, tau xy or tau yx. Please make a note of it. And what about the corresponding strain components? It doesn't matter if sigma z out of plane stress components are 0. Out of plane stress components are 0. That doesn't mean out of plane strain components are 0. That you need to keep in mind. Out of plane stress components are 0, but that doesn't mean out of plane strain components are 0. So that is what is mentioned here. Corresponding to sigma x, sigma y, tau xy or tau yx, the strain components are epsilon x, epsilon y and gamma xy or gamma yx. And what about out of plane shear components? Epsilon x, gamma yz, gamma zx. And these are the out of plane strain components, but not necessarily 0. That you need to keep in mind. Okay. So now, if you want to show these stress components in a two-dimensional or a differential element, this is how the stress components are going to look like. So out of plane stress components are 0. So only in plane stress components are shown. And what is the plane we are looking at? The plane which is passing or plane which is along the length direction and width direction. So that is along x-axis, y-axis. All the stress components are shown here. And this is an element having dimensions dx along x direction, dy along y direction. On an element having a differential element having dimension dx, dy, what are the various stress components that are non-zero? For this case of in-plane loading, they are shown here. And what about this one? These are the stress components and these are the corresponding forces. Because I want to write the equilibrium, I want to make sure that this element d of length dx, dy, and what about the other dimension? Dx, dy is the dx is along x direction, dy is along y direction, and this is a differential element. A 3D, if you the out of plane along z-axis, the thickness or the dimension along z-axis is taken as 1 unit. So it is having dx, dy, dx along x-axis, dy along y-axis, 1 unit along z-axis. Okay. For that kind of element, what are the forces that are acting on all the faces? They are shown here. And because why these forces are shown? Because I need to write the equilibrium equation for this element. That is how I am going to develop the relations. Okay. So write the equilibrium. This is if sigma x is the stress component acting on this side, and this the dimension is dx. So so you are going to have a differential stress acting on the other face, and that is given by sigma x plus the change in the stress component along this direction. So the slope of derivative of sigma x with respect to x multiplied by dx. So that is the stress component acting on this face. Similarly, other components you can easily just check it. And these are all basics which you must have studied as part of mechanics of materials. And if these concepts are not clear, better you revise your mechanics of materials background. Okay. So once you have all this, we can easily write the equilibrium equation. What is the equilibrium equation? Sum of all forces acting along x direction should be equal to 0. Sum of all forces acting along y direction should be equal to 0. If you do that, you are going to get two equilibrium equations. I hope you are taking note of it while I am explaining all this. Okay. So sum up all the forces that are acting along x direction, equate them to 0. Sum up all the forces acting along y direction, equate them to 0. You are going to have you are going to get two equations which are equilibrium equations. Okay, these are the two equations which you are going to get. And please note that what is this bx by? Bx by is the body force. Body force in this sense Body force in the sense you can assume it to be self weight. So this weight, since we are looking in two-dimensional coordinate system, so this body force also is going to have two components, bx, by. So when we are writing equilibrium condition, we need to consider this body force as well, unless you ignore this body force. Since we are writing general equilibrium equations for two-dimensional case, that body force is also included. So if you write the equilibrium equations, you are going to get this one. So please take a note of it. Please take a note of these two equations. So let's read this. The stress components acting on a differential element are shown. In addition to stresses, the figure also shows body forces, forces distributed over the volume of the body, which may be present in certain situations. What is body force? It can be gravitational force, gravitational pull, or it can be magnetic force, and or it can be a frictional force, okay, or it can be drag, okay, which may be present in certain situations, or if this force is not of significant for your analysis, then you can ignore that, okay. Note carefully the sign convention for the positive directions. On the planes farther from the origin, stress components are positive if they act along the positive coordinate directions. On the near planes, positive directions are along the negative coordinate directions. Physically, this sign convention means tension positive, compression negative. So what actually it means is here, this is the coordinate system. This is the phase which is close to the coordinate system. So here it is acting, or you can ignore that whatever description that is given here, given in that slide, and then you can take a note of it. Okay. Basically, a force which is acting away from the face, that is considered as tension. The force which is acting towards the particular face, its or surface or face, it is what is called compressive, or it can be taken as compressive force. So that is the convention that is followed. So here all the forces are shown to be acting away from the face. That means this body is assumed to be in tension. Okay. So I hope you have taken note of this this free body diagram for this differential element dx dy, and also take a note of these equilibrium equations. I explained to you how you got these equilibrium equations. In addition to equilibrium equations, you have strain displacement relations, and you have these normal strains and shear strain that we noted, epsilon x, epsilon y, gamma xy. Okay, how they are related to displacements. Strain is nothing but slope of displacement along the particular direction. So here epsilon x is partial derivative of u with respect to x. Why it is partial derivative? Because u is going to be a function of x and y. Similarly, epsilon y is partial derivative of v with respect to y. And this is cross derivative, or it is a shear stress or shear strain. Sorry, this is shear strain. So you have the cross derivatives, partial derivative of u with respect to y plus partial derivative of v with respect to x. So you please take a note of it. This is a strain displacement relation. So strains, how they are related to displacements. So we have two equilibrium equations, three strain displacement relations, and also strains are related to stresses. that how they are related. It depends on the material properties. Since we are looking at elastic material, or the materials which are within the elastic regime, two material properties are important, which is Young's modulus and Poisson's ratio. So we can characterize the material using these two independent material parameters, modulus of elasticity and Poisson's ratio. So stress is related to strain through those material parameters, assuming linear elastic material behavior. We are assuming linear elastic material behavior. That means we are assuming material is satisfying Hooke's law. That means stress is proportional to strain. So under that condition, these are the relations connecting stresses with strains. So please take a note of it. And these relations are connecting stresses with strains. We know how strains are connected to displacements. So we can express these relations. We can express these relations in terms of displacements by substituting strain in terms of displacement. So that is what, and so if you do that, you can express stresses in terms of displacements. And then you have here equilibrium equations in terms of stresses. So using the previous relations, stresses are expressed in terms of displacements. Substituting those stresses here, you are going to get equilibrium equations in terms of displacements. So that is what we require. We require equilibrium equations in terms of displacements. So we are going to substitute these relations, stresses in terms of strains, into this. Sorry, strain displacement relations. We are going to substitute into this, and then we are going to get stresses in terms of displacements. And that relations we are going to substitute into these two equations. We are going to get equilibrium equations in terms of displacements. You can go through all that. That is all self-explanatory. Okay, that is all self-explanatory. And you may surprise, what is this? This is nothing but these equations. These three equations, if you want to write it in a matrix and a vector form, this is how it looks like. These are the stress components, these are the strain components, these are the stress components which are not zero, corresponding strain components, and how they are related coming from these relations. And this is 3x3 constitutive relation can be compactly written like this. And this matrix is nothing but your constitutive matrix. Constitutive matrix is nothing but your the matrix or the relation which connects stresses with strains. And since we are discussing about plane stress case, this is constitutive matrix for plane stress case. Plane stress means out of plane stress components are zero. So with that, whatever explanation that I gave you, substituting strains, relations of strains with respect to displacement into the equilibrium, into the constitutive equations, into these equations. You can express stress in terms of displacements, and substituting that into the equilibrium equations, you are going to get equilibrium equations in terms of displacements. All that is explained here. You can go through that, and these are the two equations that you get. Please make a note of it. And you can see, you can see these equations how they are looking like. I gave you some assignment problems. I told you at that time you may have these kind of relations like second derivative of u with respect to x plus second derivative of u with respect to y is equal to something. So that is what these two equations. And please note that here this equation is second derivative of u is there here, and here second derivative of v is there. And when you have second derivative of u on the left hand side, on the right hand side you can see u and v are there. And similarly in the second equation. So these two equations are not independent, they are coupled equations. Coupled equilibrium equations. How do you solve these coupled equilibrium equations? It doesn't matter. Okay, these are the equilibrium equations. And these two equilibrium equations, using these two equilibrium equations, if you want to develop the element equation system, you need to use both these equation systems. And then you apply variational method or Galerkin method and develop the element equations. We'll see how to do that. So please take a note of these two equations. And please note that here we assumed plane stress here. Plane stress means out of this. Please note that whatever we have shown here, this is for plane stress case. Differential element is taken and all the stress components that are acting on this differential element. For plane stress case is what is we have looked at for the plane stress case. So these are the equilibrium equations in terms of displacement for plane stress case. What about plane strain? First of all, what is this plane strain? Where you encounter this plane strain? I will come back to this one, okay? What is where you encounter this plane strain case? If out of plane dimension is much longer compared to the in-plane direction, in-plane dimensions. Not only that, that is one condition. The other condition is the forces, whatever the applied load is uniform or it's constant. It's uniform along the out of plane direction. So let me take an example. I hope you are seeing this one scale here. Okay, this scale is there and I fixed here and I apply in plane load. Okay, in plane load. Please note that this scale, this is length of this and this is width of this. Thickness is there, but that is much smaller than the other two dimensions. And the forces are predominantly in the plane which I am showing you, okay? Not in the out of plane direction, not in the out of plane direction. So that is plane stress. But the same quantity or same structural component. Now, if the load is applied in the plane, that is what is plane stress. But suppose if load is applied like this in this direction, okay, then you need to you can analyze only this one, that small rectangle having width as one dimension and thickness as another dimension, and load is same everywhere. So you can use that load, and that is what is plane strain case. So please be don't be a false impression that if out of plane dimension is much longer, it is plane strain. It's not the case. It also depends on how the load is applied. You need to be very careful on that. Okay, here the load is applied in this direction, and load is same everywhere. Load is constant. And out of plane direction is much longer than it is what is plane strain. And one example is this dam. Usually people, whenever we say plane strain, they give an example of a dam or an embankment. Okay, and you can see here the section, it looks like cross section of a dam, and this is along the length direction of dam, and water pressure is going to act along this direction, and water pressure is going to be same along the length of the dam. So what is the significance of this plane strain? Plane strain in the sense, the strain in the longer direction, is negligible. It's negligible. It's almost equal to zero. So strain is predominantly in XY plane. So that's why it's called plane strain. Strain in the out of plane direction is zero. Strain in the out of plane direction is zero means normal strain in the out of plane direction is zero, or shear strain in the out of plane is zero. But it doesn't mean strain is zero, doesn't mean stress is zero. Stress in the out of plane direction need not be zero. That you need to keep in mind. Okay, so that is what is explained here. You can go through all that explanation, and this is the relation connecting stress components in plane strain components. Please note that here, in plane strain components which are not zero, strain components which are non-zero, how they are connected with corresponding stress components. That is this relation. For plane strain, the constitutive relation looks like this. So this is the only difference. So stress, how it is related to strain, is different for plane stress and plane strain, and rest of the quantities are same. Rest of the equations are same. Equilibrium equation in terms of stress is same, and also strain displacement relation is same. So whatever coupled equilibrium equations we have seen, you can develop those coupled differential equations even using these constitutive relations. And if you do that, the relations that you get, how the coupled differential equations for plane stress, how they are going to look like when compared to plane strain, that is given here. So wherever E is there, replace that E with this one. Wherever E is there in plane stress case, replace that with this one. Wherever nu is there, this is nothing but Poisson's ratio, replace it with this one, then you are going to get corresponding equations, coupled differential equation for plane strain case. Okay. Sorry, here here it is written, solving plane stress problem when plane strain formulation is known, solving plane strain problem when plane stress formulation is known. Just now, whatever we noted is coupled differential equation for plane stress. So replace E with this one and mu with this one, you get corresponding differential equation for plane strain. And if you want to reverse that, you can use this one. Okay. So this is the equivalence between plane stress and plane strain problems. So that is how you get the coupled second order differential equations in terms of U and V. And now, okay, we have two differential equations which are second order. We need to solve these differential equations. So we require two boundary conditions to solve it. What are the two boundary conditions? This is second order differential equation. So first, those boundary conditions of order 0 are essential boundary conditions. Those boundary conditions of order 1 are natural boundary conditions. But this problem, this is a structural mechanics problem. We know that we can either specify the displacement boundary condition or force boundary conditions. So what are these displacement boundary conditions? What are these force boundary conditions? In mathematical language, displacement boundary conditions are nothing but zeroth order differential equations. So they are essential boundary conditions. And force boundary conditions are going to be first order. They are going to be natural boundary conditions. And then whether these force boundary conditions really result in first order differential equations. And if you have doubt on that, that is clarified here. Okay, so let's read this. These are second order differential equations. Note that two equations are coupled and the solution must be obtained by solving the two simultaneously. And essential boundary conditions are displacement boundary conditions U and V specified, and natural boundary conditions are derivative of U and V specified. But we usually specify the forces, whether the forces are really the derivatives of displacements or they are functions of derivatives of displacements. That is what we will see the equivalence here. So Tx, Ty are the components in x and y directions. Tx, Ty. Usually the forces are also referred to as tractions. Traction is nothing but force. Traction in the x direction and traction in the y direction. It's nothing but force in the x direction, force in the y direction. Okay. Please note that this xy coordinate system is some coordinate system we define for our convenience. Okay, we can also define some other coordinate system if required. So the components of these forces can be with respect to x and y axis or with respect to some other axis. So x and y, suppose I have a plane, inclined plane like this. I have an inclined plane like this, a wedge is shown here, an inclined plane, and x and y axis of this. And if I take this plane, let's assume instead of calling it as a plane, let's first of all, where do you get this? Suppose you have a boundary, you have an element boundary, you are solving a problem. While solving that problem, over a part of the boundary, you need to apply the forces. Over the part of the boundary, you need to apply displacement boundary conditions. Here we are talking about the part of the boundary over which you are applying the force boundary conditions, distributed load or pressure load, or it can be point load. Okay, so the actual boundary can be curved like this. Actual boundary can be curved like this, but when you use finite element discretization, this element, the actual boundary is going to be idealized in this manner. And you can see here on the actual boundary, normal keeps changing. Out of plane normal. The normal which is pointing outwards keeps changing. On the idealized boundary, if it is a straight line, it almost remains constant. It remains constant. Outer normal remains constant. Okay. So this is the actual boundary. This is the idealized boundary. So I'm showing that boundary here. On that boundary, forces are acting. Forces in the x direction, force in the y direction. Instead of usually, please note that this xy coordinate system, depending on each individual, you can define different xy coordinate system. But the forces, how do you say on a particular structural component you have certain forces? How do you specify that? Usually we are going to specify whether we are applying force tangentially over the surface or normal to the surface. So usually instead of because each of you may use different xy coordinate system, so I don't know which xy coordinate system you are using, so I cannot say specify what is tx ty. Tx ty depends on you, the design or whoever is analyzing the problem. But the actual thing is we are going to specify the force tangential to the surface or normal to the surface. So that is what is this one. Force applied tangential to the surface, that is denoted with the TS. Force which is applied normal to the surface, that is denoted with TN. So how this TS, TN are related to TX, TY? How these normal forces and tangential forces, they are related to component of forces along X and Y direction, or how tractions along tangential direction, normal direction, they are related to tractions along X and Y directions. They are given here. The relation is given here. And they are in terms of direction cosines. So you can go through this, and please note that you need to spend some time here. And what is this nx and y? Nx and y are defined in terms of this, whatever is shown here. Nx is nothing but here. Nx is nothing but, or nx is nothing but x component of normal, ny is y component of normal. And how this nx and y are calculated, they are given here. Nx is nothing but dy over ds, ny is minus dx over ds. Why this minus? You can see here, we are going in the negative x direction. We are going in the negative x direction. So how do you get dx, dy? If you know, let's say this is a part of an element, this is the actual boundary, and this is idealized boundary. I know this idealized boundary is a straight line, and then I know this starting point. I know a node here, a node is going to be here. Ending node, I know the coordinates of this node, I know with respect to x and y. Coordinate of this node, I know x with respect to x and y. So once I know the coordinates of these two nodes, I can easily find what is dx, dy. Okay? And also what is ds. So that is all what is written here. You can go through that. So this relation, these two equations gives you relation between tractions along x and y, the components of traction along x and y directions, how they are related with respect to normal and shear components. Okay, so you can go through all this. And also TS is nothing but traction on this differential element or on this surface, on this face. What is the traction along x direction? Traction, you can imagine traction like a pressure. Traction is like a pressure. If I want total load, Tx is the component of traction along this. If I want the total force along x direction, Tx times what is this? What is the area on which it is acting? Please note that we are looking at a two-dimensional case. Out of plane dimension, we are assuming it to be unity. So Tx times ds times 1 unit is going to be giving you total force acting in the x direction. And that you write the equilibrium equation. Sigma x is the stress acting on this face. Sum of all forces acting in the x direction should be equal to 0. So sigma x times dy times 1 unit is going to be the force acting on this on this face, and tau xy times dx times 1 unit is going to give you force that is contributed from the shear components that is acting in the x direction. So this is nothing but your equilibrium equation for this element. Okay. So if you divide this entire thing with ds, and then you can develop this relation. So how this traction is related to internal stress components. How this traction Tx is related to internal stress components, that is given here. Okay. So now we noted two things. How traction components with respect to different coordinate system, they are related, how the traction components, they are related to the internal stress components. Here Tx is related to sigma x tau yx via this relation. Similarly, Ty is related, Ty is related in this manner. And here the stress sigma x is expressed in terms of the strain components as well as displacement components. So Tx becomes this one, Ty becomes this one. Why we have done all this exercise? Just to check whether these tractions, I just introduce you to this word traction, whether these tractions are really involve derivatives, first derivatives of displacements or not. So that is what is verified here. Okay, that is what is verified. So to solve this second order coupled second order differential equations, we require essential boundary conditions which are UV and specified tractions. Okay, so let me quickly go through, give me 2 minutes. So we have the entire background that is required for solving two-dimensional elasticity problems. So all this we covered. And please note that XY, Z or XY coordinate system, it depends on each of you. Let's say 100 students are there in the class or 50 students are there in the class. So 50 students can adopt 50 coordinate systems and get solve the problem and get the stress components. Okay, get the stress components. But each of you, with respect to the coordinate system that you selected, you may give me what is sigma x, sigma y, tau xy. So I'm going to get 50 sets of sigma x, sigma y, tau xy values for the entire problem. So how do I synthesize that? So usually what we do is, instead of talking about the stress components which are dependent on the coordinate system, we are going to we are interested more on stress components which are independent of the coordinate system. They are nothing but principal stress components or principal stresses. So how you can go back to your mechanics of materials, how the principal stresses are calculated once sigma x, sigma y, tau xy are known. So that is what is actually revised here. That is what is actually revised once again. So I don't want to go through this. You can go through all that. Okay. So you must have studied as a part of your mechanics of materials all these equations. You please go and revise all that. Once you get principal stress components, you can define failure theories, or you can adopt one of the failure theories and check really whether the component is safe or not. Okay, so that is what this one is. Okay, so now we are ready to we have the coupled second order differential equations, and we have the essential boundary conditions in terms of displacement, natural boundary conditions in terms of tractions, which are nothing but functions of derivatives of displacement. So now we are ready to solve the problem. So you can take these two coupled differential equations, adopt whatever we studied, variational concepts and Galerkin concepts, and then develop the equations. But really that is not required, because if you are good in structural mechanics, then you can easily write the potential energy functional for this problem. So potential energy functional is nothing but strain energy minus work done by the applied forces. So if you are able to write this potential energy functional, you are going to get what is equivalent functional in your variational method. So that is what is written here. Okay. So strain energy minus work done by the applied forces. Strain energy, how you are going to get? Area under stress strain curve multiplied by the volume of the body. So that is what this one is. Area under stress strain curve, halves epsilon or sigma times epsilon. But please note that that is for scale, assuming uniaxial strain and uniaxial stress. Here you have three components of stresses, three components of strains. So that it is going to look like this: half epsilon transpose sigma or sigma transpose epsilon, it doesn't matter, and integrate over the volume of the body. That gives you total strain energy. So what I suggest is you can go through all this with whatever explanation I gave you. You can go through all this, how strain is related to stress, all that is substituted. Finally, the strain energy is expressed in terms of strains. Okay, and thickness, outer plane thickness, here it is assumed for generality, it is assumed as h. But when we are solving the problem, we can assume h to be equal to 1 unit. Okay, this is for plane stress and plane strain. For both cases, you can make use of this strain energy. And what about applied work done by the applied forces? Traction times displacement, force times displacement. Force times displacement is going to give you work done. Which force? X component of force has to be multiplied with X component of displacement. Y component of force has to be multiplied with Y component of displacement. So that is what is written here, and that has to be integrated over the surface on which the force is applied. Please note that here this is the segment, or this is the face on which force is applied. I told thickness, outer plane thickness is 1 unit, but just now for generality we assumed it to be h. So h is going to be there constant everywhere. H times integrate this force component multiplied by the displacement component. Similarly, this force component Ty multiplied by the displacement component, integrate along this h. That gives you the work done by the applied forces. Instead of Tx, Ty, you can also write in terms of Ts and Tl. So that is all what is written here. You can go through it. Okay. So once you have all this, you can easily write what is potential energy functional. So we'll discuss about this in the next class. So if you do that, if you substitute all this, potential energy functional is going to look like this. Potential energy functional, you can substitute this. What is this U? You can substitute from here, and W you can substitute from here, and this is going to be the potential energy functional. When I say this is the potential energy functional, is you don't need to believe that this is potential energy functional. Similar to what we have done earlier, this potential energy functional, you can take the variation of it and go in the reverse direction and check whether really this is potential energy for that two coupled second order differential equations along with the boundary conditions or not. So that is what is verified here. Verified functional. We can go through it, okay? We can go through all this, and indeed that is the potential energy functional. So with all that, so you can go through it. With all this, we have all the mathematical background that is required for solving. Now we need to decide which element we want to use. So we already noted various kinds of elements. We will make use of these elements and try to work out some problem in the next class. Okay. So I gave you an assignment 7, and with whatever we covered, you should be able to solve 1 and 2 problems, and third problem you should be able to solve in the next class, by the end of next class. Okay. So so we have 3 more classes left, and I'll try my best to complete as much as we can. But please note that whatever background that is required for you to understand finite element analysis or finite element concepts, that you already have it if you have done the course and assignment properly. Okay. So we'll continue in tomorrow's class, and let me take attendance. Okay, thank you.